we made a robot arm that juggles. We modeled everything in the simulator with physics like gravity and friction, as well as the limitations of the robot to achieve the perpetual juggling motion. With some additional work, we could even load this program onto a real Ewa robot and have it juggle in real life.
Pick and place is one of the core applications of robotic manipulation. In its simplest formulation, it's a static problem. The objects aren't moving when I'm trying to pick them, and there aren't strict timing and velocity requirements for putting them down. In this video, we'll show you how we took standard pick and place to the next level by requiring that we pick the objects at a specific position with a very specific velocity at a specific time, also known as catching, and place the objects at a specific position with a specific velocity at a specific time, also known as throwing.
For our physical setup, the object we are juggling is a rigid ball that has the same dimension as a squash ball. The arm we've chosen is a Kuka Iwa. It has a reach of 0.8 meters, a load capacity of 7 kilograms, and have 7 degrees of freedom. The gripper we're using is a WSG 2-finger gripper by the Wise Robotics. Notice that juggling with 2 fingers here is like trying to juggle with chopsticks. It will force us to be really precise when throwing and catching.
To start, we need to choose a point at which we're going to throw and catch. The approach we use to find such two positions is forward kinematics. We first decide on a set of comfortable joint angles of Iwa, and then calculate the corresponding spatial position of the gripper. Let's explain more about what we mean by comfortable. Each joint adds one dimension to the configuration space. Given Iwa has 7 joints, we're imagining the whole space of allowable joint configurations as a 7-dimensional volume. What we want is for the throw and catch positions to be well within that volume, not at the boundary, so that we can reach any nearby position. So now that we have our throw and catch positions and their comfortable joint configurations, we'll use a formula of projectile motions to calculate the start and end velocity given the max height of the trajectory. We also want to get corresponding joint velocities. We first calculate the Jacobian matrix for translational velocities at the joint configuration. By multiplying the pseudo-inverse of Jacobian with the spatial velocities, we're able to obtain the joint velocity for both catch and throw.
And now it's time for the cool part. How do we get our robot to go from being here with this velocity to here with this velocity at exactly 0.639 seconds later? We can frame this as an optimization problem. We want to minimize the length of the path, subject to the following constraints. First, we constrain the positions and velocities at the throw and catch points. Second, the entire duration of the arm trajectory needs to be exactly the duration the ball is in the air for. And third, we ensure that the joints on the Iwa robot don't exceed their position, velocity, or acceleration limits. So perfect! We now have our position trajectory at every point. We now know what joint position commands we want to send to the robot arm.
At this point, we've done a lot of the groundwork. We're super excited, we put it on our robot, and this is what we see. Everything is going great, then it lets go of the ball at completely the wrong position with the wrong velocity. Graphing the desired positions and velocities, as well as the measured positions and velocities, we see that the measured values lag behind the desired values by 0.0538 seconds. 0.0538 seconds sounds like a really small delay, but given the precision that we need, this small delay leads to a big error. To solve this problem, we need to peel back the layers of the onion and see how a position trajectory gets translated into the force commands sent to the Iwa. Originally, we were sending our desired positions to a system that interpolates the desired state with discrete derivatives. The desired state is then fed into the inverse dynamics controller, which spits out the force commands to send to the arm. Note that this system doesn't feed desired acceleration to the inverse dynamics controller at all. To improve tracking, we removed the state interpolator and took analytical derivatives on our position trajectory to get our desired velocities and accelerations, and fed those into the inverse dynamics controller directly. We can see that with these changes, the measured values now converge to the desired values.
We put our new controller on the robot, but somehow it is still not able to catch the ball. Marking the actual throw position with the blue sphere and actual catch position with the pink sphere, and comparing them to the planned throw and catch positions marked by the red and green spheres, we see that they don't match exactly. And the gripper is trying to catch the ball where we thought it was going to be, instead of where it actually is. To account for this, We need to change our planner so that it updates the trajectory based on the actual position and velocity of throwing right after releasing the ball. We also need to calculate the ball position and velocity at the catch time given throw position, throw velocity, and time duration. Noticing that all the velocity and position that we just measured and calculated are spatial, we convert the predicted catch position from a spatial to joint coordinates using differential inverse kinematics. We put this on the robot, and after some debugging, finally it works.
We tried a bunch of different heights and found that it can juggle up to 2 meters high. To make the jump to juggling multiple balls, we had to modify our planner. When trying to juggle 2 balls, after throwing the first ball, you have to catch and throw the second ball, all in the time that the first ball is in the air. So we have much less time to move between the throw and catch positions. We can keep most of our planner exactly the same, but after a ball is thrown, instead of replanning the trajectory based on the ball you just threw, we update it with the position and velocity of the ball that we want to catch. And this is what it looks like. One thing we had to do was to warm start the arm with the desired joint velocities at time 0, because unlike in the one ball case, it didn't have enough time for the actual velocities to converge on the desired velocities before it had to throw the ball. Next, we tried juggling 3 balls, but kept running into the problem of the balls colliding in the air with each other, because now there are 2 balls in the air at the same time, and because of the slight inaccuracies in the throw. We were about to give up when we decided to try making the balls smaller, and it worked. On one hand, this feels a bit like cheating, but on the other hand, it's also cool because our controller is precise enough to juggle something so small. This was the limit though. The kinematic trajectory optimization kept failing when we tried to juggle 4 balls.
And finally, to put it on the real robot, we need a perception system. In the simulator, we can always know the exact position and velocity of everything, but in the real world, we'll need to find a way to measure that. We simulated 3 Intel RealSense depth cameras where we plan to combine the point cloud from each camera, then subtract the gripper from the point cloud. By best fitting a sphere to the leftover point cloud, we would be able to estimate the center position of the ball from the fitted sphere, where we would then be able to feed the position to the kinematic trajectory optimization function. In this project, we only managed to get the stage of extracting the point clouds from the cameras, but haven't yet been able to subtract the arm or fit the sphere. For future work, we would like to further improve the system to have the robot juggling more balls, or even objects with different shapes, where we need to consider the orientation of the object for selecting the grasp. We would also like to give the robot additional flexibility on choosing when to catch instead of constraining the time duration between catch and throw. Furthermore, to integrate the system to the real robot, we will need to finish our work in perception and then develop a controller that's robust enough against camera noise and real-world disturbances that might change the ball trajectory.